Say hello, I'm David. I'm the coordinator of the Maths Learning Centre. Welcome to the 2020 Semester 1 Maths 1B revision seminar. If you're watching this from the future, well, hello from during the COVID-19 2020 pandemic, which is why you're doing this from my room. We've had a couple of requests about Taylor series and L'Hopital's rule and directional derivatives, and we'll see what we can get through. For those watching on video, there were other people around me here, but I've blocked them out with some boxes so you can't see who they are. Cool. So what I'm going to start with is I'm going to share the notes. I'm going to find what the notes say about Taylor series errors, and hopefully we can ask them what would happen if questions and try out some variations of problems based on what's in the notes. So I'm going to find Taylor. All right, so now we're looking at alternating harmonic. Hello, we're just starting to have a look at Taylor series at the moment, and we're on recording, so welcome. If you have any further requests on top of Taylor series, L'Hopital's rule, or directional derivatives, feel free to pop them in the chat, and feel free to interrupt me if you've got any questions. Okay, so this is what Taylor series are. The point is to make it look like a polynomial, but it doesn't have to be x to the power of something. It could be x minus c to the power of something. Here it is. That looks more like a polynomial there. And to figure out what these coefficients are, you're supposed to do derivatives. There we go. That coefficient is the nth derivative with the c subbed in divided by n factorial. And a Taylor series goes forever. And my understanding is that a Taylor polynomial is what you get when you stop instead of going forever. So I'm just scanning my way through this, just having a look at what I can see. Having a look at what I can see to find the errors at the moment. So I could search for error now, but I'm just seeing what I can see in the notes. Okay. So here's the thing that's a little bit about errors, I guess. It's got sine x is equal to these things plus something in the order of x to the 7, or x plus something in the order of x cubed. Oh, here we go. Taylor's remainder. This is the thing with errors that we're talking about. Is this the thing? Okay. Thank you. So that's the thing that we're talking about. All right. I'm just going to draw on it so that I can show you what I'm looking at. So this thing here. So Taylor's remainder theorem. If you've got the nth order Taylor polynomial, then the error is this for some value of psi, which it doesn't tell you what it is, except it does tell you it's between x and the c and the x. Okay. Cool. All right. So, okay, cool. Thanks for bearing with me while I figure out what's happening here. Oops. So this is the sort of question that you're talking about here. Find a bound for the error if using a Taylor polynomial of order n centered at x equals 0 to approximate the sine function. Okay. Cool. I'm just looking a little further to see what I've got. Binomial series. Oh, and that's it. And then L'Hopital's rule is the very next thing. Okay. All right. I'm going to switch over to drawing my stuff. So I'm going to stop sharing that for the moment. And I'm going to turn on my document camera. It's going to replace my face. So you might need to hover over me and pin my video so that it's the video that you can see, so that it's really big, because it's going to be my document camera. There's a lag in the voice and in the video if I use two video inputs at the same time. So I'm just going to do one at the same time. So this is my document camera. If you hover over that, there should be some dots where you can click to pin this video to make it bigger. The chopping board there just allows my computer to be just a little over the edge of the desk. All right, that's not too bad. Okay. So because I'm working from home, I'm not going to be able to share these notes. So if you want me to slow down or put something back, please just ask. So the idea is that if you've got a function, it should be possible to rewrite it as like this, plus a2 x minus c squared plus a3 x minus c cubed plus forever. And that's called a Taylor series. What? Sorry, my computer has just said that it's not plugged in, even though I think it is. Give me a second. Okay. Yeah, let's try this one. Ah, here we go. Oh, okay. So is it blurry when I'm writing, or is it blurry all the time? This is the only one I've got, I'm sorry. Just trying to change the focus. That's really bad. Yeah, sorry, that's the best I can do with this one. I'll try and write big. Okay. In fact, what I might do is I might just turn my page so that it's easier for me to know that I'm supposed to write big. So if I've got a function, then I can make the the nth Taylor series for that, Taylor polynomial for that, will be like A1, and it'll go all the way up to here. It's going to be like a polynomial. And these coefficients are found by doing the nth derivative at the point C divided by n factorial. That's how I think about what a Taylor series is. So you've got all these coefficients, but it's basically a polynomial with x minus c's instead of just x's. And you figure out what these coefficients are by doing this calculation involving derivatives. And that's the nth Taylor polynomial. And you want to know how far away your function is from the real one. And so you go this thing where the real function is its nth Taylor polynomial plus the nth error. So if the error is positive, that means that your Taylor polynomial is too small and you have to go up to get to the real answer. And if the e is negative, then that means you have to go down from the Taylor polynomial to get to the real answer. And Taylor's remainder theorem says that the error is equal to this, the n plus 1th derivative at some number psi, but we don't know what it is, over n factorial times x minus n plus 1 factorial, x minus c n plus 1 to the power of n plus 1. For some psi between x and c, then that was really badly written. So that's the theorem as I know it. So the idea of the theorem, as far as I'm aware, if I'm just remembering this correctly, and I just have to say these things aloud to myself whenever I do this every semester, because I can't remember it without telling myself the story. And it's one of the things that I used to do in exams as well, is figure out a way of saying it to myself so that I could remember what was going on, or so that I could understand it if I saw it written on a piece of paper. So if you're doing in an exam, essentially open book version, then you need to know when you look at it what you're looking at. And you actually, it's probably quicker overall to just know it so you don't have to look it up. I know it's polynomial, I know the coefficients come from the derivatives, and I know that I'm imagining back in the day before there were calculators and graphics things that drew graphs for us and those sorts of things. And even today, when we have to teach the computers to do these things, we need ways of telling how bad our estimate is without actually knowing what the true answer is. And that's what this provides. So if you wanted to figure out exactly how far apart your Taylor polynomial and your function were, if you were able to calculate this function without using a Taylor polynomial, you could just subtract them to figure out what the difference is. But if the only way you have for calculating this function is to use a Taylor polynomial, you'll never know what the real answer is. And so this formula provides a way of knowing how badly wrong your estimate is without knowing the real answer. That's the idea. Looks like it's blurrier on the corners, so I just need to make sure it's right in the middle. Okay, so that's the idea of this. And so your classic problem asks you to find formulas for the error, or to figure out how close you have to be to a specific value x to get the error that you want, or how high n has to be to get the error that you want, or any of those sorts of things. Now I'm just going to ask the people who are here, which of those sorts of varieties of things do you find the one that you just is the most confusing? So the sort of thing where you have, I'm just going to write them down. You know what the function, and you want n so that the error is less than a number, or something like the x so that the error is less than a number, or a formula for what En is. Which of these is the sort of thing that you'd like me to try and do an example of? Feel free to pop it in the chat or just say out loud. I'm going to call this number 1 and this number 2 and this number 3. This one here. Yep. Cool, that's at least 2 people who want me to do that. Cool. So you want a formula for this based on, that's like a formula that uses n. That's the sort of thing that we're going for. Sweet. Right, well, let's do it. So I just need to think of an example. If anyone has one off the top of their head, feel free to tell me, but otherwise I'm just going to come up with one. Ah, right, so sort of like an upper bound for ENX, that sort of thing. Okay. Yes, someone was mentioning that earlier. E, you said that right at the beginning, didn't you? Okay. Let me just think. Classic. I'm just going to see what happens. This is going to be my function. And I'm going to go the error in the nth Taylor polynomial. I don't know if it's going to be like this, but I'm just going to see what happens. Most of the complicated questions begin with needing to do that, so I just wanted to start out with that. So often you've been told what the x is, and sometimes you're left with just an x that's just unknown. The nth Taylor polynomial with what's the center going to be? That c that's referring. It's tradition to use 0, but you don't have to. I could pick a different center just to see how that works. Let me choose. I don't want to make it too hard for myself. I'm just going to see what happens when I do this, because I can always try a simpler one later. With center pi on 4. So what that means is that the Taylor polynomial, the nth Taylor polynomial, is going to be like a0 plus a1 x minus pi on 4 plus a2 x minus pi on 4 squared plus, and so on, a n x minus pi on 4 to the n, where a n is the nth derivative. Oh, I shouldn't have called it y. Can I call it f of x? Yeah, it's the nth derivative of f at the point pi on 4, because that's where the center is, over n factorial. Okay. And normally you'd see that in some notation. Oh, I can't use n. Damn it. Let's call that m. Right. Can't use n for both because that's confusing. You don't know which one's the end and which one's the one that you're changing. But it's totally okay to write it like this. Okay. I have an equals. Oh yeah, that should be an M2, I guess. Thank you. This AN is just that last one. Yeah, whatever. So I had someone saying you guys should do it as an AK, but it's easy to change an N to an M by adding an extra loop. So I like doing that. Okay, so that means that the nth error is this, but a little different. It's going to be the n+1th derivative at pi on 4 over n+1 factorial, but it won't be at pi on 4. It'll be at some other number. That's what the nth error is going to be. It's going to be exactly this, but all the m's are now n+1, and this pi on 4 isn't a pi on 4 anymore. It's some other number. Between x and pi on 4. Okay. That's what the error is. So the only way to find a formula for the error is to find the n+1th derivative. So I'm going to need to find the derivative. So let's see. The 0th derivative is the original function. The next derivative, the first derivative, sine will become cos. The 2 will come out. And the second derivative, the 2 will still be there. The cos will become a minus sine. And then because of the chain rule, the 2 will come out again. So I'm going to have -4 sine of 2x. And then the third derivative, I'm going to have -4. The sine will become a cos. But because of the chain rule, I'll have to times by 2. So, actually, I don't want to keep that as a 4. I want to keep counting how many 2's there are, because I've got a 2 times 2 here, and then a 2 times 2 times another 2. So I reckon that's going to be a 2 squared. And this is 2 times 2 inside the 4, and then another 2, so that's 2 cubed. Okay. Cool. And so I think we're going to get a pattern here, because now that we're back to the 4th derivative, we've got a -2 cubed. The cos will become a minus sine. And because the chain rule will multiply by that 2, so we're going to get a minus minus, so it's going to get a 2 to the 4 sine 2x. So and then now when I do the next one, there's going to be there's going to be a plus, and then there's going to be 2 minuses, and then there's going to be 2 pluses, and then there's going to be 2 minuses. And so that's how that seems to work. Wow, this one's going to be complicated. I don't like it. Well, all right, I'm committed now. So it looks like fnx is going to be, this is not a very good answer at the moment, but it's going to be plus or minus. It's going to have a 2 to the power of n, because this 4 is a 2 to the power of 4, this 3 was a 2 to the power of 3, this 2 was a 2 to the power of 2, this 1 was 2 to the power of 1. It's going to be 2 to the power of n, and it's going to be sine or cos. Well, that's all going to be dependent on That's all going to be dependent on where we're up to in the sequence, because it flips between sine and cos and sine and cos. Okay, so it'll be sine. Every second one will be sine and every other one will be cos, so that's good. So this will happen when n is even, and this happens when n is odd. And then the plus or minus, it goes plus plus, then minus minus, then plus plus, then minus minus. That's going to be a bit tricky to figure out. Okay. Normally you don't want a formula for the error, but just the absolute value of the error. So I might be okay to not have to worry about that plus or minus in the end. I feel like if my lecturer gave me this question in an exam, they would probably specify that the n had to be like 2n or something, or 4n or something, so that it would be easier to tell where what was going on here. I feel a bit bamboozled here. I'm just going to stop and ask if people, how people are feeling about this, and if they'd like me to try and find an easier example, or if they want me to battle through with this. Because I just made this one off the top of my head and I didn't know if it was going to be a good one or not. Or if you have any questions about what I've been doing so far. All right. Cool. Easy one, please. I will say that most lecturers would be asking for the absolute value. And so the question would actually be the absolute value of En, in which case the absolute value is not going to make, these pluses and minuses aren't going to make any difference to this. So it is going to be sine or cos, depending on which one I have, but I don't know which one it's going to be. So if you don't mind, I will do an easier one as well, the person who asked me just before, but I'm going to see if I can rescue this. Because what if they wanted not a formula for this, but an upper bound for that? No, can't be bothered. It's just, I think you could, this question could be rescued if it was asked in a certain way, if your lecturer asked this in a certain way, but I don't think I can right now. At the moment though, there is still something we can learn for it. Yep, upper bound for the error though, gotcha. There's still something I can learn from this, and it is that I can, if I noticed that I kept multiplying by 2s, and so instead of writing down what the actual answer was, I wrote down what 2 to the power of, I put it in terms of 2 to the power of, so I could see the connection between the derivative I was up to and the formula that I was doing. Yeah. Okay, so let me just do a really specific one with actual numbers in it for finding the upper bound for the error. So let's see. I'm just going to keep with the same function, but say find an upper bound for the absolute value of E5x. Just give me a second, I'll do 1.5. Where ENX is the error in the nth Taylor polynomial at pi on 4. Okay, so we're going to still use the same function, sine of x, but we're going to find an upper bound for a specific error, the absolute value of the error in the fifth Taylor polynomial centered at pi on 4 at a specific x, which is 1.5. So normally there'd be an x in this position, but but we are going to be doing it for a specific number. So the thing that when I read this and when I imagine this in my head is that here is my 1.5. Or maybe I shouldn't have done 1.5. Maybe I should have done pi on 2. Here's pi on 4, which is about 0.78. And I've got sine of 2x, which looks like whatever it looks like, and I'm interested in how far my Taylor polynomial is from the correct function. So maybe like this is the Taylor polynomial, and this is f of x, and I want to know how far apart they are. That's the idea that we're trying to figure out. Okay, so to do this, I still need to find the sixth derivative because the error formula is still, according to the theorem, the next derivative evaluated at some point divided by the next factorial. It's still that formula. So because I want E5, this is going to be a 6 and a 6 and a 6. So I still need the sixth derivative. So I already went to all the effort of finding various derivatives. I got up to the fourth derivative. So I'm going to need to do the sixth derivative. So let me move all that crap out the way. It's so much easier in a lecture theatre, it has a better quality document camera and more space. So I'm sorry about the fuzziness of this. So we would do this, we'd go f of x is sine of 2x, and f dashed of x equals blah, and f double dashed of x equals blah, and then we already got to earlier the fourth derivative, which came out to 2 to the 4 sine of 2x. And then the fifth derivative, well, the sine will become a cos, and the 2 to the 4 will times by another 2. And then the sixth derivative, the cos will become a minus sine, and the 2 will come out, and so we get a 2 to the 6. That's the sixth derivative. Okay. So that's what the sixth derivative is. And so my fifth error is going to involve that sixth derivative. So the fifth error will be the sixth derivative, which is this, but not at x or c, but this unknown number psi, divided by 6 factorial x minus pi on 4 to the 6. So what I've done is I had this formula before, and I've replaced the formula for f6 with the formula that I just figured out what it was. Okay, we're doing all right. It's not the best. The fifth error at the point 1.5 always put too many loops on my size. Is that? And then I guess now I need to start estimating it. So yeah. I do know that this psi is somewhere between 1.5 and pi on 4. So this zone here, that's where the psi is, somewhere in there. So psi is definitely a positive number. I don't know whether the sign is positive or negative in that zone. I do know one thing, that the absolute value of E5 certainly won't involve this number here. And this is positive, and this is positive, and this is positive. So that's going to, and the minus will go away. So I'm going to get a 2 to the 6 over 6 factorial. The absolute value of sine of 2 psi times whatever 1.5 minus pi on 4 to the 6 is. So I've gone as far as I can, I think, without trying to estimate what sine of 2 psi is. So I have some ideas. Sine of 2 psi is always less than 1. So I could try and make this more accurate if I wanted. If I knew whether this function was increasing or decreasing on this zone here from 1.5 to pi on 4, then I would know where the maximum of this thing is. So the biggest error that this could possibly be will be dependent on how big that is. So the largest possible error happens when sine of 2 psi is largest. For me, that's the biggest idea in this section. When I'm doing problems in exams or in any situation where I'm on my own and I can't ask for help, I like to have things I can hold on to tightly, things that I definitely know to be true, that I can say to myself to help get myself back on track. And this is one of the things I say. I look at this and I say, when will this be the largest it can possibly be? And it will be the largest when this is the largest it can possibly be, because everything else is always the same, no matter what psi is. So I need to figure out a value of psi that will make this the biggest it can possibly be, because that's the largest it could possibly be, because I don't know what psi is. So I think of all the options that it could be and pick the largest answer for this. Okay. So I'm not 100% sure how to do that. I've got two options here. I could do a really, really bad estimate, or I could do a slightly better one. So, you know, bad estimate. So bad estimate, well, sine of anything, no matter what it is always less than 1. And so I could say that this thing is the largest value this could be is 1, and I could replace that number there with 1. So I'm going to do that whole thing. Bad estimate, that's always true. And so therefore, the estimate for 1.5 is always going to be less than or equal to 1. Like that. And so I would just put that in my calculator. 2 to the 6 is 64. 6 factorial is 720, I think. Where's my factorial button? Must be here somewhere. Yeah. 720. Okay. 64 divided by 720 times 1 times 1.5 minus pi on 4 to the power of 6, 0.01. So when I do my 6th Taylor polynomial, the error is less than 0.01. So I'm definitely within 2 decimal places. Like I'm within, yeah, which is pretty good actually. Oh no, not within 2 decimal places. Sorry, 2 decimal places would be 0.005. But I'm pretty close. I'm within 0.01 of the correct answer. So we could get a slightly better estimate, I reckon. I wouldn't do both of these in an exam. If I was in an exam, I would just do this. I could get a slightly better estimate by trying to get a better handle on what sine of this is within this zone here. So let me just sketch sine of 2x. So sine of x would normally go like that. And 2x would be shrunk inwards. So normally sine would do this at pi, but 2x would do that at pi on 2. And normally sine would do this at pi on 2, but 2x would do it at pi on 4. And we're at 1.5, which is in this zone here. Oh no, there isn't a better estimate. Sorry, I was wrong. We're looking at this zone of the graph just here, and the maximum value of sine on that zone is in fact 1. So it's not a better estimate at all. Yeah. But basically I would pick whichever of these is the highest, and that would be the biggest the answer could possibly be. Cool. So I would like to pause at this spot and say, does anyone want me to talk about anything that I just did there? Feel free to write something in the chat or just turn on your microphone and talk. So good question. Should we always assume it's 1 when doing error bounds? No, only if it's sine or cos. So the reason it is, it's because it's sine or cos. Because it's sine that's always less than 1. So maybe it would be useful to do an example where it doesn't come out to 1, so that we can make sense of what's happening there. So how about I do one where it isn't 1? That was an excellent question. Thank you. That sort of question where it's like, is it always this way? Is a really good question. So how about I do another one where it doesn't come out that way? Find an upper bound for the I don't know, let's do the fourth one at 3. No, I don't want to do 3. Up 1, where ENX is the error for the nth Taylor polynomial at x equals 0. Okay, let's do this one. So we've got the 4th error, so we're going to need the 5th derivative to do that. So the original function is ln of x plus 2. The first derivative would be 1 over x plus 2 times the derivative of the x plus 2, which is 1, so that's okay. And since I'm going to differentiate it, I'm just going to write it like this. And then the next derivative is minus 1 times x plus 2 to the power of negative 2. Okay. And then the next derivative is minus 1 times minus 2 times x plus 2 to the minus 3. And then the 4th derivative is minus 1 times minus 2 times minus 3 times x plus 2 to the minus 4. And the 5th derivative, which is the one we wanted, would be minus 1, minus 2, minus 3, minus 4, x plus 2 to the minus 5. Now, since I actually only want this specific one, it would have been okay for me to figure out what these numbers were, but I just noticed that I'm able to make a point about trying to come up with formulas for these things. The reason I didn't multiply any of them out is so that I could see the pattern. When I look at this, I see that it's got a 1. This one's got a 1 times 2. If I ignore the minuses, this one's got a 1 times 2 times 3 times 3. This one's got a 1 times 2 times 3 times 4. I can see this as having a 4 factorial as part of it. And this one has a 3 factorial as part of it. And this one's got a 2 factorial as part of it. So that allows me to come up with a formula for what the derivative is, which means that if I want something that involves an n, then it might be useful. So I just wanted to show you that that's a thing. I haven't quite finished yet because you'll notice that I only multiplied the 1 and the 2 and I didn't take into account the minuses. So there's 2 negatives there, which means it's minus 1 squared. And there's 1, 2, 3 here, so it's minus 1 cubed. And there's 1, 2, 3, 4 here, so it's minus 1 to the 4. So that's how I would create a formula for the nth derivative that I might use to try and figure out a formula for En as opposed to E4. Does anyone want to ask about that? All right, cool. So I found my 5th derivative, which I don't need the 4 factorial anymore. I can just write it as 24x plus 2 to the negative 5. And so that means that the absolute value of E41 will be E4x. We know that that's the 5th derivative at this number psi over 5 factorial times x minus 1 to the 5 for psi between x and, no, it's not x minus 1, it's x minus 0. Just a second. The center was 0. Okay. So this is the center here. Okay, between the center, which is 0 and x. And so that formula we just figured out is this. So we get that. So we're almost there. Whoops, sorry. Why am I doing that? And that x is actually a psi, isn't it? Because we've replaced the x with psi here. All right. And the x we're thinking of is actually the number 1. So the absolute value of E41 is 24 psi plus 2 to the negative 5 over 5 factorial times 1 to the 5. Doing well. Well, this anyway. For psi between 1 and 0. Okay, well, we're doing okay. We can do a little bit of work here. The absolute value there, that's a positive number, that's a positive number, that's a 1. And psi is between 1 and 0, so it's positive. So psi plus 2 is positive. So this whole thing is positive. And so that's also just going to come out to this. And I'm going to move it to the bottom if that's okay. Because it's easier for me to think about how big it is when it's on the bottom. And 5 factorial is 120, and so these are going to cancel, and I'm going to get this. Okay, so that's what I've got. So the question is, how big could this possibly be based on what I know about the number psi? Because psi is between the center and the number I subbed in here. So the only way for me to know for sure is to know about how this function behaves. When it was a sine, I knew that the answer was always 1 for the maximum. But for something like this, I need to think about what this function looks like. Now, it's 1 over something to the power of, so it's going to go down like this. When xi is 0, I get 1 over 5 times 2 to the 5, which is a number, and then it only gets smaller. So this is the shape of this graph. So the maximum happens back here when psi is 0. So this is decreasing. For psi equals 0. And so therefore my E41 is less than or equal to what I get when I put in psi equals 0. Which is 1 divided by 5 times 2 to the power of 5. 6.25 times 10 to the minus 3. So 625. That's in the 10 to the minus 3 position. 3, 2, 1, 0. Okay. So that's how I would decide if I had a function that didn't have an already known upper bound. It looks like we're nearly at 2 decimal places there. So thoughts on that? Thank you. All right. So let me just go back over that. It's important to sort of stop and reflect on what just happened. So what happened with this one is that the beginning was the same. The only way to figure out what the error is to find the next derivative after this number. And so I figured that out. It was possible to find a pattern, but it wasn't necessary. But that might be necessary if I needed to do E14, because I could skip all this work and skip straight to what it would be, copy the formula based on what it looks like here to do the 14th one. Okay, so that's that part. And then I did as much work as I could before I started making decisions. So I got it all the way down to here before I started to think, well, what is the biggest this could be? And the only way to tell would be to look closer at what this function does. The 5 probably doesn't make a difference to where the maximum is, so I could have just looked at that. And then I pick the value of psi that makes this the biggest it can possibly be, and then I know this is less than or equal to the biggest it can possibly be. Yeah. This decision here, for what this answer is, that answer comes out to, was really easy for sine, because this answer is always 1 for sine. Yeah. Sure. Can you tell me what that, I've had someone say there was a Mobius question like this, and could we go through that? Definitely. As long as you can tell me what it was, I can give it a go. While you're looking it up, I'm just going to check my email to see if anyone else is trying to get in here and can't find the password. No, it's looking all right. All right, give it a second. This is what I've got from you. Oh, very similar, wasn't it? So mine was a 2 plus 1, mine was an x plus 2, and this one's got a 1 plus x. The degree n term in the Taylor series around x equals 0. Oh, okay. Well, why don't we do this for my question, hey? Since I've gone through part of the effort already. Okay, I'm just going to, well, let me just have a quick look at what's here. So the degree n term, and then I think they're using z instead of psi because they can't get you to write psi in the computer. Upper bound to the absolute value. And then how many terms are needed? Okay, I'm going to keep that open on my screen so I can keep track of what questions I'm doing, but I'll keep doing it on this one with the x plus 2 if that's okay, because I've already done half the work and we don't want that to go to waste. Okay, so I've already done some of this. No, I'll do the one that's actually in the Mobius because it's not going to be that different, and I just want to make sure that we can check our answers against what Mobius said the answer was supposed to be. So they had ln of 1 plus x. So the first question in that photo was find the degree n term. Okay, so around x equals 0, that's the center. And so we know that the Taylor series is like a polynomial, so it'll be like the Taylor series will go like f of x equals a0 plus a1 x minus 0 plus a2 x minus 0 squared forever, but the am or an or whatever it is going to be the nth derivative at the center, which is 0, divided by n factorial, like that. And so the term, the nth degree n term, is that coefficient times the matching thing, like that. All right. So we need to find the nth derivative, and we're going to have to find a form when n x is 0, when nth derivative when we sub in x equals 0, and we're going to have to find a formula for it in terms of n. So I think we need the nth derivative first. So the first function is ln of 1 plus x. F dashed x is 1 over 1 plus x, which is 1 plus x to the negative 1. And then we're going to get the same thing happening that happened last time. The second derivative is going to be minus 1 plus x to the minus 2. The third derivative is going to be minus 1 times minus 2 times 1 plus x to the minus 3. The fourth derivative is going to be minus 1 times minus 2 times minus 3 times 1 plus x to the minus 4. And so I reckon we're almost up to the point where we can make a guess at what the pattern is. So the nth derivative, so if we look at this, this 4 has a 1 times 2 times 3. That's a 3 factorial. And it has 3 negatives multiplied together. And it has a 1 plus x to the minus 4. And so the nth derivative ought to follow the same pattern. So it should have a -1 to the power of something, and this number 3 is 1 less than the derivative we were up to, so that's n-1. And then it has a 3 factorial, which is also n-1, and then it has a 1 plus x to the -4, and that number is the same as the derivative I was up to. So that's n. So that's the formula for the nth derivative. Technically, this formula only works when n is greater than 0, because the 0th derivative is ln, and it doesn't make sense to have, yeah, this is not correct for n equals 0. Okay, so it does work all the way back to here, I think. -1 to the 0 is 1. 0 factorial is 1. Yep, okay. Works all the way back to the first derivative, n greater than or equal to 1. Okay, and then I need to know what fn of 0 is. That's -1 to the n-1, n-1 factorial, 1 plus 0 to the -n, which is -1 to the n-1, n-1 factorial times, well, 1 to the power of anything is 1. And so that's the answer for fn of 0. Cool, we're doing well. That's for n greater than or equal to 1. I guess that f of 0 is just ln of 1 plus 0. It's ln of 1, which is 0. Okay. Okay, so what do we need? The degree n term. We need to divide by n factorial and times by x minus 0 to the n. So the degree n term. I'm going to write the degree n coefficient first. The degree n coefficient is just this number here. And so that will be fn 0 divided by n factorial, which is -1 to the n-1, n-1 factorial divided by n factorial. Sweet. Now this is interesting. n-1 factorial will be what I get when I multiply all the numbers between 1 and n-1, like all the whole numbers. And this one is all the numbers from 1 to n, so mostly they contain the same numbers. In fact, this would be 1 times 2 times all the way up to n-1, and this has one extra number, which is n. So most of them are going to cancel out. And I'm going to get a -1, n-1 over n. I mean, to cancel out isn't a real maths word. Technically, I'm dividing the top by n-1 factorial and dividing the bottom by n-1 factorial. Okay. So that's degree n coefficient, and so the degree n term would be this coefficient times x minus 0 to the n. So that's my degree n term. Would anyone like to say something about this before I move on to the next part of this question? Okay. So next question on my photo, thank you for sending that, is the error term, the en. So number 2, enx. Okay, I want a formula for this. Okay, well, the error term, according to Taylor's theorem, would be the next derivative over the next factorial x minus center to the next power. But normally we put the 0 in this spot, but we have to put some unknown number. Okay, so in Mobius, they ask you to put a Z in this spot because they can't ask you to type the letter psi because it's not on your keyboard. Yeah, but on paper, you'd normally use the letter psi to match with what your lecturer did. Okay, cool. So we need the next derivative. So we know that the nth derivative of x was Where was our formula for that? Here it is, just here. So okay, just copy that out. Okay. And so the n plus 1th derivative should be exactly the same, but with an n plus 1 instead of an n. So n plus 1 minus 1 would be n. N plus 1 minus 1 would be n. And n plus 1 minus 1 would be n. Sorry, there is no minus 1. There's just an n, and it's supposed to be an n plus 1. And it's not an x, it's a psi, isn't it? Okay. So that's this part of the formula. And so then En of x will be this thing divided by the n plus 1 factorial times x to the n plus 1. Which is, so we do the same trick, like the n plus 1 factorial contains all the numbers that go together to make n factorial. And so that's going to be an n plus 1. Well, that's what it is. It's not pretty, but that's what it is. And so in Mobius, you would put a z in that spot. So I guess if you wanted to feel like it was marginally simpler, you could write it like this. Because a negative power, multiplying by something with a negative power, negative exponent is the same as dividing by that thing with the positive exponent. Okay, well, that's my formula. The third question is upper bound for absolute value when x is greater than 0. Okay. Of the error. Okay, well, the absolute value of the error is the absolute value of this. Oh, this thing, damn it. What was the whole point of me writing that out if I wasn't going to copy it? Okay. And, well, the minus 1, whether it's plus or minus 1, if I do the absolute value, it will just be plus 1, so that's not going to make a difference. And the n plus 1 is a positive number already because it's a whole number, and so that's fine. That's not going to be changed by the absolute value. And the 1 plus, well, the sigma, don't really know what this psi is, but I guess I do know that psi is between x and 0, because that's how it always works. So if x is positive, then the psi is in here, and so it's positive as well. Okay, so therefore psi is positive. Okay, cool. So this is a positive number as well. The only thing we don't know about, we do know that x is positive. So if x is positive, that's all good. Everything's positive. And since absolute value can affect each thing in a multiplication and division separately, I can just turn it into this. Okay, rightio, I'm doing well. If I didn't know whether x was positive or negative, then I wouldn't really know whether this was positive or negative or not. and I wouldn't know whether this was positive or negative, so I'd have to put an absolute value there. But since I do know that x is positive, I don't need to worry. All right, what's the next question on my list? Use this formula to find how many terms are needed to estimate ln of 1.4 with an error of less than 10 to the minus 8. 4. How many terms ln of 1.4 with error less than 10 to the minus 8? Okay. Sorry, that's bad writing. I'm sorry. So let's see, the original function was ln of 1 plus x. So that means that f of 0.4 is ln of 1 plus 0.4, which is ln of 1.4. Okay, so the x that we're thinking of is 0.4. So the error n, when the x is 0.4, we know that the absolute value of that... Oh, I didn't have an upper bound. Sorry, everybody. I haven't actually finished this question yet. Right. I haven't actually found the upper bound. I've just found what the error is at the moment. That's what the actual error is. I've been asked to find an upper bound for it, which means that I want the biggest that this error could possibly be based on what the value of x currently is. So if the x is a specific x I'm thinking of, then this bit and this bit don't change when the psi changes. So the thing that makes this the biggest will be when this is the biggest. So largest when 1 over 1 plus psi to the n plus 1 is largest. Now 1 over something to the n plus 1 would go like that. And if we go like that, and if we add 1, that's the same as shifting it over like that. So it's this shape. So the x is here, and the psi is in here. And this is 1 over 1 plus psi to the n plus 1. Like I say, this is decreasing. So the maximum value is when psi is 0. So therefore, the absolute value of the error is less than or equal to what we get when psi is 0. Oh, 0. So that's my upper bound. Okay, cool, rescued. So now that I have an upper bound, the whole point of the upper bound is it doesn't involve the psi. So if they do ask you for an upper bound, you know that you're supposed to produce something that doesn't have a psi or a z in it. It's only supposed to involve the x and the n. Or it'd just be a number if you knew what x and n was. Okay, let's try that again. So the last question was how many terms are needed to estimate it, which means we need to know what the n needs to be. So we've just figured out that the x is 0.4 in this situation. So we can use our error term estimate for the error, which we just figured out was x to the n plus 1 over n plus 1. All right. So we want the absolute value of the error to be less than 10 to the minus 8, because that's what they want. So the only way for us to guarantee at the moment that this number is less than 10 to the minus 8 is to make this number less than 10 to the minus 8. If this is less than 10 to the minus 8, then this is less than that, and this is less than that, so therefore this is less than that. So in my head, I'm imagining just here a less than 10 to the minus 8. That's what I'm imagining. I don't normally write it on my piece of paper, but that's what I'm imagining. So if I can arrange this to be less than that, then this will be less than that as well. So choose n so that 0.4 to the n plus 1 over n plus 1 is less than 10 to the minus 8. So now there is no formal way of solving this. It's something that involves both powers and division, which is annoying. If it was just powers, then I'd have a chance. I could use logs to solve this. And if it was just division, then I could use multiplication and division to solve this, but it's both. And so it's not going to be accurate. The quickest way is probably to just start guessing n's and keep trying them until you get one that works. We can make a quick guess. This is about a half, and I know that a half to the power of 10 is a thousandth-ish, is about, 2 to the power of 10 is 1024, so is about a thousandth, and 1,000 divided by 10 would be 10,000, so we would be a 10,000th, so that'd be 10 to the minus 4, so we're only about halfway. So even if the n was 9, we'd only be about not quite down to the level we want. So my guess is that I'm going to need something about twice as much, but I don't really know for sure. The other way is to try it without the n plus 1 and see what you get, and then know that it would have to happen before that. So I'm just going to try this. So if I did ln on both sides, I get n plus 1 times ln of 0.4 is ln of 10 to the minus 8. And so the n plus 1 would be ln of 10 to the minus 8 over ln of 0.4, which would be ln of 10 ln of 0.4 is about 20. And so my n's got to, if without this n plus 1, that would get us up to 19 for n, 20-ish. I'm thinking that since we are dividing by n, it's going to happen a little earlier than that because we're actually dividing by something. So I'm going to just try a number. Let's just try things. So let me just try maybe 15. I don't know how much earlier to go. So 0.4 to the power of n equals 15, so that'd be 16 divided by 16 is 2 times 10 to the minus 8. So 15 is not quite far enough. So we're doing pretty well. So let me try it with one higher number. It's not quite there yet. Because we want it to be definitely less than 10 to the minus 8. So I reckon if we go to the next one, oops, delete. We get, yeah, now we're far enough. Which is now 3 0.8 times 10 to the minus 9. Okay, so this is now small enough, which is less than 10 to the minus 8. So we need to go up to the degree 17 term. Right. Took me a bit, but I got there. So could someone say something about that? I'm glad that was really helpful. Look, I'm going to have to finish now, but don't forget that the Maths Drop-In Centre is open virtually. There's a special My Uni course. I sent a link to it in the original email, and I'll send it again when the recording's ready. So you can drop in any time between 10 a.m. and 4 p.m. And there will be a Zoom. There will either be a Zoom meeting already open that you can join, or you can put a note in the discussion board to say, hey, I would like to talk about Maths 1B, and maybe be specific about what you want to talk about, and someone will be there to talk to. So any other questions that you might have, you can pop in and talk about that. We're open 10 a.m. to 4 p.m. Monday to Friday, all the way to the end of the exam period. So let me just put my face back on. Yeah, so pop in and say hi. You've still got a little while to your exam, so just keep, whenever you want to talk to someone about your maths, you can go to the virtual drop-in centre and someone will be there to talk to. The Maths 1A exam and the second year differential equations exams are finished now, so it's mainly Maths 1B and Maths 1M left. So there should be someone to talk to about your maths. And don't forget, there's also revision seminars. All the past ones are on your page of the Maths Learning Centre website. And when this video is ready, I'll send you a link to where the video is going to be. So thank you for coming. Good luck. I wish you the best on your exam when it comes.